Okay, so let's get started then. Okay, recap. So last time I took the last two classes I spent the last two classes to talk about PyTorch and how to, the autograd backpropagation of the modules, the RNN, and the actually re-implementing RNN to the actual vanilla RNN version, not the naive version. And hopefully, I hope that was enough, so that everybody is now familiar with PyTorch. At least they feel like they can do something with it, and how to train them. Well, I didn't talk about how to. Oh, okay, I see. I guess I didn't talk about how to train your module or train your network on GPU, but you can easily find them on the online tutorial, PyTorch tutorial. So hopefully, I hope that was like enough of a tutorial or enough of a teaching, a lesson for PyTorch. Right, so we're gonna go through a bunch of interesting topics, more theoretical topics from now on. And I mean, of course, if you have any question regarding PyTorch, you can always ask them in class and more to me during the class. But yeah, there won't be too much like practice parts or demonstration classes anymore, unless you explicitly ask for them. So okay, so interpretability today. So far, what we've done is we've talked about the EHR actual data and how to pre-process them for two prediction tasks, the readmission prediction for, so hospital readmission and ICU readmission. So we talked about how to set the task, how to set the criteria for extracting patients from EHR, and how to train the logistic regression, and then step forward, how to train or how to use RNN to model longitudinal EHR for predicting stuff. So now that we've talked enough about the prediction part, it's now time to move on to a more different aspect of predictive modeling in healthcare. So one of which is interpretability. A lot of students probably attended the seminar from Tuesday, so like the day before yesterday. So in that seminar, I briefly talked about my model, my project for interpretability, which was retain. So we're going to go over that today, but it'll be way more in depth. So we're going to derive all the mathematical equations and know how to make it interpretable and all that details. Yeah, if anybody was curious about how to make RNN like fully interpretable, then now is the time now is when you get your question answered. All right, so interpretability, we'll start with logistic regression versus neural network. Why some people say logistic regression is interpretable with neural networks or not. And then there are mainly three approaches in my perspective. So one, like how to interpret or how to explain neural networks, there are mainly three approaches. One is gradient-based approach. The other is attention-based approach. And in the attention-based approach, we're going to talk about retain, which is the project that I did a couple years ago. And then there are the third approach, which is model agnostic approach. So agnostic means it doesn't care about which model that you're using. It's a meta level type of thing. So whichever classifier or model that you're using, whether it's SVM or trees or neural networks, doesn't matter as long as you have like for example like shapely value. It doesn't matter which model you're using. You can still somehow interpret or explain what your model is doing using Shapley value technique. Or Lime is kind of a recent approach. It was not that recent, I guess, because Lime was presented in KDD 2016, so it's already 4 years old, but it's a very popular method. And again, like if you use Lime, then doesn't matter what classifier or what model you're using. You can just still apply Lime to whichever black box model you'd like. All right. So, I mean, briefly just touching on the philosophical aspect of interpretability. So some people say the interpretability, or a lot of people do not fully agree what interpretable models are. Like, what does it mean that your model is interpretable? It's a very subjective, subjective like issue, or it's a subjective definition. Like, anybody can call their model interpretable by just somehow showing what their model is doing under the hood. And for example, a famous healthcare researcher named Zachary Lipton, and he has a pretty high impact paper called the mythos of interpretation, or interpretability, I forgot. And in that paper, he discusses that logistic regression might not be that interpretable compared to neural networks when you're using like millions and millions of features. For example, if you are using millions of features but your model is linear, technically you can like study the coefficients, the weights for each feature, and see the impact of see the correlation of each feature to the final prediction. But if there are a million features, then are you actually going to go through all the features, like every single one of them, and try to explain your model? That's very unlikely. It's not practical. So still it's an open issue, interpretability. Okay, so we're going to start with logistic regression, why some people call this the most interpretable model. Or it could be any linear model, but I just took logistic regression. It could be SVM. It could be naive Bayesian. Yeah. All right. So if you recall, logistic regression is this kind of architecture. So you have the raw data that represents something. In our case, it represented a visit or encounter, and then you just feed it into a. You can think of it as a single neuron with a sigmoid activation function, and here I'm just taking a subset or subsection or one feature, which is marital status, from our raw feature vector. And so if so every single dimension or every single feature will be tied to a specific weight, and there will be W0, W1, W2 starting from so each, like, let's just say that the first dimension of marital status is single, second dimension is married, third dimension divorced, fourth widowed, and fifth other. And I briefly touched upon this subject when I was introducing logistic regression, that like if you study the coefficients, then you will learn the correlation. So if, for example, W3, after you've trained your logistic regression, W3 happens to be positive, then what does that mean? That means that when you're single, so only you can take only one value out of 5. Like, you can't have like 1, 1, 1, 1, 1. You can't be at the same time be single and married and divorced. That can't happen. This is a categorical value. So only one thing can be true. So for example, if you say, I mean, if the model turned out to have a W3 as a positive value, then what does that mean? That means that when you're single, then you are more likely to, I guess if we take the readmission prediction task, then a hospital readmission prediction task, then when you're single, you're more likely to return to the hospital, like be readmitted to the hospital. I mean, this is just an example, so it doesn't, I'm not sure if that's true, but that's how you interpret logistic regression. If W4 is negative, then that means that when you're married, your likelihood or the probability of you returning to the hospital or being readmitted is lower. So it's negatively contributing towards the final prediction. So it's kind of like you can think of it as just a contribution factor, because what you're doing is you're just multiplying every single feature. I mean, in the logistic regression, what you're doing is basically you're multiplying every single feature to its corresponding weight, and then you're summing them up, and then you're pushing that through a sigmoid function, the nonlinear activation function. So it's pretty easy to interpret. But when you start adding like hidden layers between the input layer and the final output, so this is one hidden layer feed for a neural network, and we're using, let's say we're using sigmoid function as a activation function for the hidden layer. And in this case, then, how do you interpret the weights? Like, if your V11 and your W1 is positive, what does that mean? Like, You can't say that the first, let's just say this is, what was that? That was admit type, yeah. So if this is like the regular or elective, and this is emergency, and this is other type of like different types of admission to the hospital. So if the the V11 and W1 are both positive, then can you really say that elective admission type, if you come to the hospital just by yourself, not by emergency, but by like voluntarily, or you've planned your admission, then you're more likely to return to the hospital, like more likely to be readmitted. Can you really say that just because like both of these are positive? Because this feature also impacts other neurons too. It contributes towards the output by this line here, 1 2 W2 and 1 3 W3, 1 4 W4. So just studying individual like weights doesn't work, and it's harder to interpret like by studying individual weights. No, it no longer applies. So like even like you can't just break it down into like 4 different cases, because whatever you do here, you're not whatever like analysis you do on V11 and W1 doesn't, you're not taking into account what's happening in other weights. So yeah, so way harder. I guess it's you can try to approximate it. You can, I mean, with just a single hidden layer, you can go through all the V's and all the W's and just try to come up with like an average effect or average impact the first feature has, the elective admission type has, towards the outcome. So you can like average them out or something like that, or you can sample or something like that. But still, there's no like accurate way to interpret them. And the reason, I mean, the important part is that there is a sigmoid function here. This nonlinear activation is what makes the entire thing very difficult, because without the nonlinear activation, you can just simply combine these two matrices and make them into a single matrix. Maybe I can write down what I'm talking about. So the first matrix is what? It's like 40,000 by 4. So 40,000. Let's draw it like that. So this will be 4 here. This will be 40,000. And this is your input, like 40,000 single, 1 by 40,000. And you put it through, I guess the, yeah. Yeah, I can write it. I can write it here. You put it through the first weight matrix, and then after that, you put it through a nonlinear activation function. But let's assume that there is no nonlinear activation function. And the next thing is you are putting it through a 4 by 1, not a matrix anymore, because you have a single output, but you have like you put it through a 4 by 1 vector, a weight vector. And if there is no sigmoid function between here, like these two, then what you can actually do is you can first like if you're familiar with like all the linear algebras, like 101 stuff, doesn't matter how, like which operation you do first and which operation you do like later. These are all like matrix multiplications. So you don't have to do this first. You can do this first, and if you do these operation first without the sigmoid function, if you just multiply these two matrices first, then what you're left with is a very long, like 1 by 40,000 dimensional vector with a like this. So this will be 1 basically. This will be 40,000. And then you get a single scalar value like 0.5 or whatever. So this is what happens. So what this tells us is that if you don't have a sigmoid function, then theoretically, there's no difference between learning two separate weight variables or two separate weight matrices compared to just learning a single weight matrix, or in this case, not a matrix, like single weight vector. There's no difference between the two. So this is like, no matter how many linear layers you have, without the nonlinear activation function, you're basically doing you're just basically learning a single linear operation weight matrix or weight vector. So that's why it is really important to, like, if you want to increase your model capacity, or if you want your model to do to approximate a very complex function, then it is very important to put a nonlinear activation function. These days, most of the time using ReLU. All right. Yeah, I guess this is more like a fundamental, like very basic explanation of neural network and why they use a nonlinear activation function. I forgot to mention that when I was like couple lectures ago. Anyway, so that's, yeah, so the existence of the hidden layer makes the interpretation really hard. And as you increase more layer, it's virtually impossible. Like with only one hidden layer, you can somehow try to manage to like average the effect of a single feature, and then, you know, try to explain away. But if you have like this many layers, it's virtually impossible to study all the weights and all the weights and all the weights. So yeah, more hidden layers, less interpretable, or that's so did a lot of people believe. Now so gradient-based approach or gradient-based interpretation of your model is most of the time used in computer vision. So if anybody's familiar with like image processing or computer vision, this will be very easy for you. I'm not going to go through the details anyway, because we're not dealing with images. Maybe in the second half of this course, AI810, we can talk about images like for a couple of lectures. But this lecture is not about how to process images. So I'm just gonna show you some pictures, what it means to do like gradient-based interpretation. Right. Can anybody see? Wait, is everybody seeing what I'm seeing? Did I share my desktop, or did I? What up? Oh, I was only sharing my PowerPoint. Okay. All right. Can everybody see the cat screen? I mean, not the cat screen, the cat images. Yes. All right. Cool. So we're typically talking about like inception models, or LUNet, or AlexNet, or those kind of like very big, heavy vision models, or even ResNet. I think in this case, the author was using VGG16, which is also a very popular model. So, and it has a lot of layers. VGG16 is like 1, 2, 3. Well, I mean, yeah, like pooling comes right after conv. So there's like 1, 2, 3, 4 layers, and then another feed for neural network, drop, dense, like maybe 6 or 7 layers. Anyway, all right. So I'm not going to go into detail like what convolutional neural network is, but it's just a way to process images to make the machine understand what the contents are. So if you have a cat image, there are three things basically you can do with gradient-based approach. I mean, yeah, there are 3 different ways you can try to analyze your model with gradient-based approach. One is simply just so ConvNet has something called filters, or like you can push the cat image into your neural network and then try to print out the intermediate values, because there are hidden layers in neural networks. So it's the same with ConvNet. So you can try to just visualize or print out the intermediate values from the hidden layers and see what it is doing like in the intermediate processes. So that's this picture here. Like I think this is the first layer activation. So first hidden layer activation value. It's just it's almost exactly the same as the input, the cat image, which is this. Then you print out some other stuff. And as I said, convolutional neural networks has something called filters or kernels, and that you use a lot of different filters. Like sometimes you use like 32 filters, sometimes you use 64 filters, and you generally each filter on their own learns to focus on different aspects of images. So in the first case, maybe like the edge of the eye or edge of the ear is what the first filter is focusing on. This one more on the like the actual like the pupil of the cat eye. That's more highlighted. You can see the difference between this and this here, right? And so the author did proceed to print out all the different like cat images in different layers. So like this is a first layer, second layer, third layer, and if you are familiar with like the very first Google Brain paper and like a deep learning model where they try to learn the image of a cat using a lot of YouTube images, YouTube videos, they actually show you progressively that as you move on from the lower layer like neural networks lower layer to the higher layer, it starts to learn different stuff, different things. So in the lower layer, the model focuses on the like the very the pixel level features. And as I said, different filters will focus on different stuff about the pixels. So some focus more on the background, and some focus on the face of the cat, like face of the cat here, like face of the cat here as well. This one particularly focusing on the eyes only, and the others are like all like greened out or blacked out. And as you move, like this is second layer, it's not that different, but in the third layer, now it is focusing more, like we can interpret that it is focusing more on different parts of the cat. So here, like some filters are focusing only on the eyes, only on the ears, like some different focus on the ears, something like that. So, or eye and the ear. Like this very much looks like the essence of a cat to me. This one, not so much. It's basically like a bright filter. Like this one is exactly the opposite of this one. So not all filters learn helpful stuff, but you can see that they try to learn different aspects of the catness, like what it is to see a cat or to perceive a cat when an image is given. Right. Now, yeah, this is the final layer. This is way more abstract than before. Like it's using, like the resolution is even lower. Like these two kind of like circles are probably the cat eyes. This one's scary, I guess. This one's, it doesn't even have an eye in it. Anyway, something like that. So this is one way to interpret your model. The other is try to do a backprop on your input. So what you do, the typical way to use backprop is to train update the parameters of your model. But what if you fix the parameter? Like once you've trained your neural network to make it like to be like a perfect classifier, perfect predictor, then you can fix the parameters or the weights of your neural network and try to do a gradient descent on your input actually. So now the values of your input, in this case, the pixel values, will be the parameter, and you're updating it so that you can maximize the output of your model. So it's like it's like a reverse. Before the input was fixed and the parameters of your model were changeable or updatable. But now what we're doing here is the models are fixed. The model is fixed. The model parameters are fixed, and you're updating. The inputs are updatable, and how you update them, you're using gradient descent. And what's typically happening here is that, like as I said, Confident has different filters or different. You can think of filters as like different neurons in the hidden layer, and you're trying to maximize. You're trying to like update your input to maximize the output or maximally activate each single neuron or each single filter in your convolution. And if you do that, then you get a filter like this. I mean, you get an input like this. So this is the very first layer. Like there are a lot of filters in first layer. Oh, there's a question. 일반적인 방식으로 생각했을 때 인간 해상도 높을수록 사물 더 건강에 좋은데 스피드 생성이 된다고 나왔나요? 그리고 이미지 프로퍼레이션의 경우 픽셀을 위아래 좌우 어떤 관계를 Okay, I'll just first answer this in Korean and then repeat that back in English. 해상도가 높을수록. 근데 이제 우리가 보통 해상도가 높다 그러면은 굉장히 큰 이미지 막 8메가픽셀짜리 무슨 뭐 그런 옛날에 똑딱이나 아니 요즘 뭐 핸드폰 이미지 같은 게 굉장히 이제 이미지 픽셀이 큰데 그게 똑같은 사람을 구분할 때 해상도가 높은 거랑 아니면 그냥 이미지 사이즈 자체가 엄청 커가지고 해상도가 높은 거랑 약간 다르다고 볼 수 있거든요. 그래서 이제 내용을 많이 담냐 아니면 내용을 하는데 그냥 디테일이 엄청 많냐 이제 그걸 나눠봤을 때 내용이 너무 많고 너무 크면은 막 이미지가 막 거의 뭐 60cm에 막 50cm다 이렇게 한 화면에 잘 들어가지도 않는다 이런 거면은 이제 애초에 너무 힘들고 그게 아니라 사람 한 명 아니 똑같은 얘기죠. 이제 그 안에 내용이 많냐 적냐의 차이라고 보면 이제 그냥 한 사람의 이미지가 한 얼굴을 분간하는 클래시파이어를 만들 때 어떤 이제 뭐 굉장히 해상도가 높은 사람 얼굴을 가지고 분간할 수도 있고 굉장히 해상도가 낮은 뭐 128 x 128 같은 사람 얼굴 가지고 분간할 수도 있는데 사실 사람 얼굴이냐 아니냐 그러니까 이제 그 휴먼 페이스 디텍션 같은 경우는 해상도가 그렇게 높을 필요가 없어요 애초에. 그러니까 해상도가 높으면은 그만큼 처리를 많이 해야 되거든요. 지금 이 컨브넷의 이제 구조를 제가 말씀을 안 드렸는데 이게 어떻게 되냐면은 그 이제 조그만한 뭐 한 3픽셀 바이 3픽셀짜리 필터 같은 게 이렇게 쭉 이미지를 이렇게 그리드로 훑거든요. 이렇게 왼쪽에서 오른쪽 쭉 한번 훑고 그다음 아래 픽셀을 내려서 또 왼쪽 오른쪽 쭉 훑고 이렇게 쭉쭉쭉 훑어야 되는데 그 말인즉슨 해상도가 클수록 훑어야 되는 근데 이미지 크기도 커지고 시간도 많이 걸리고 그거를 이제 이렇게 계속해서 압축하거든요. 보통은 이제 이미지가 이제 예를 들어서 뭐 256 by 256이었으면 그걸 그 다음에 뭐 한 200 by 200, 그 다음 뭐 150 by 150 이런 식으로 쭉쭉쭉 압축을 해가지고 나중에 그거를 계속 압축을 한 다음에 한 1000 정도의 사이즈로 만들어서 그걸 소프트맥스로 돌리는데 그렇게 하려면 이제 그만큼 예를 들어서 뭐 막 100만 by 100만짜리 픽셀이다 그러면은 그만큼 그걸 압축을 엄청 많이 해야겠죠. 그러니까 모델 사이즈가 엄청나게 커져야 돼요 한 번에는. 그래서 근데 사람 얼굴을 이 사진이 사람 얼굴이냐 아니냐를 분간하는데 그렇게 높은 해상도가 필요가 없거든요 애초에. 그냥 128 by 128이어도 충분해요. 왜냐면 사람 얼굴하고 뭐 개 얼굴이나 고양이 얼굴은 이게 서로 다른 거라는 거, 다른 종이라는 거를 128 by 128 정도의 픽셀만 있어도 충분하기 때문에 그렇게 그 약간 오버 인포메이션인 거죠. 해상도가 너무 높을수록. 그래서 굳이 그럴 필요는 없다는, 그러니까 뭔가 하여튼 항상 이제 좋은 밸런스가 중요하다는 거랑 그 다음에 비슷한 현상, 그 히든 레이어 크기를 줄이지 않기도 하죠. 레즈넷 같은 경우는 이제 리시듀얼 네트워크 같은 경우는 그 옆에 뭐 그것도 이제 뭐 설명하려면 한참 더 걸리는데 그거 같은 경우는 일부러 그 히든 사이즈의 크기를 전혀 줄이지 않거든요. 이제 그러니까 적어도 컨브넷을 막 쌓을 때는 컨브넷에서 50개를 쌓든 100개를 쌓든 컨브넷 내에서는 전혀 이제 이미지의 크기를 뭐 줄이진 않아요. 이제 블락별로 조금 말씀드리기 이렇게 뭐 이거 뭐 레즈넷 설명을 드려야 돼가지고 이걸 하려면 하여튼간에 뭐 그렇지 하여튼 뭐 그런 방식도 있습니다. 이제 히든 레이어의 사이즈를 줄이지 않고 마지막에 가서 소프트맥스 넣기 전에만 이렇게 콱콱콱 줄이는 뭐 그런 방법도 있긴 한데 뭐 어쨌든간에 줄이긴 줄여야 돼요. 이렇게 뭐 그래서 뭐 256 by 256이면 벌써 그게 한 5만 디멘션쯤 되잖아요. 실제로 곱해보면 그 5만짜리를 바로 소프트맥스에 넣으면은 이게 잘 안 되기 때문에 결국에는 이제 마지막 클래시피케이션을 하기 전에는 이렇게 어쨌든 압축을 하는 경우가 대부분입니다. 그래서 네, 그게 첫 번째 답일 테고 그 다음에 이미지 레코그니션 같은 경우 픽셀의 위아래 좌우 어떤 관계 이제 좌우랑 위아래는 사실 오히려 괜찮아요. 왜냐면 이제 컨브넷의 필터 특성상 아까 말씀드렸듯이 3x3짜리 또는 5x5짜리 필터가 이렇게 훑으면서 쭉 가기 때문에 이게 국소적으로 어떤 피처가 있는지가 중요하지, 얘네가 뭐 이게 어디로 요만큼 그렇죠. 이제 그러니까 이게 애초에 5x5, 3x3 필터를 이용한다는 의미 자체가 뭐 사진에서 눈이 있냐 없냐를 구분하는 그 정도, 그러니까 그런 정도의 굉장히 로컬한 정보에 굉장히 치중을 해가지고 그걸 합쳐서 이제 최종적으로 분류나 또는 예측을 하겠다는 얘기를 해가지고, 그게 뭐 이게 좌우가 반전돼 있다거나 아니면은 뭐 그런 거에 크게 이게 굉장히 로버스트해요. 그런 약간 트랜slation 인베리언트하다 하는데, 그거를 이미지가 약간 다 오른쪽으로 쏠려 있거나 뭐 왼쪽으로 쏠려 있거나 뭐 위로 올라갔거나 올라갔거나 뭐 좌우 반전이 일어났거나 이런 경우에도 굉장히 잘 되는데, 뭐 이게 뭐 예를 들어서 약간 뭐 한 90도 돌아갔다 이러면 조금, 이미지가 90도가 돌아갔다 이러면 이제 그거는 조금 새롭게 볼 수가 있거든요, 컴퓨터의 특성상. 그래서 그런 경우는 일부러 90도 돌린 이미지를 넣어줄 수 있어요, 데이터셋에다가. 그냥 이것도 똑같은 사람 얼굴이니까 이것도 잘 해라 이런 식으로. 뭐 이제 그런 걸 이제 데이터 오그멘테이션이라고 그러는데, 90도 돌린 이미지, 180도 돌린 이미지, 또는 뭐 일부러 약간 노이즈를 뭐 흰색 노이즈를 좀 뿌려줘가지고 이것도 어쨌든 사람 얼굴이다, 뭐 그런 기법을 쓸 수가 있죠, 좀 더 로버스트한 모델을 만들려면. 네. 혹시 답변이 됐나요? 네. Okay, so just briefly to recap in English, the question was that should we use a higher resolution, just like humans humans are more humans get more information out of high resolution images. Is it still a good idea to use high resolution images? I'm confident, and the answer is it depends. So if you're doing as simple task as human face detection, you don't really need that high resolution images. 128 by 128, or even like 64 by 64 is okay. So you don't want to like overdo your task. And there was also a sub question about not not compressing your images. Okay, so did I just like, was I just disconnected? What happened here? Can everybody hear me now? Right, okay, so yeah, the internet connection is really weird. All right, sorry about that. Yeah, I'm using, yeah, I really need to change my internet provider. All right, as I was saying, so yeah, the question was, is it a good idea not to compress your hidden layer, just to like preserve the resolution of the image? And the answer was some architectures do that, like residual connection, resnets. They don't contract or they don't compress their hidden representations up until a certain point, but it's just like different strategy. And final, what was the final question? Let me could you repeat the final question? What was the final question? 재영님, 아까 여쭤보신 것 중에 마지막 성웅님이었나요? 재영님이었나요? 그 마지막에 여쭤보신 질문이 뭐였죠? 아, 맞아요. 픽셀 위아래. 아, 예, 감사합니다. Okay, so the last part of the question was, does it matter, or like it seems, so the question was, it seems important to care about the position of the pixels, like whether certain pixels, the relationship between like patches of pixels, like whether they're like scaled, like they're translated to upwards or downwards or left side or right side. And the answer was that because of the nature of convolutional filters, it is translation invariant, so it doesn't really matter whether you slightly tilt your picture towards right, to the right or to the left or to the up, to the down, but rotation is a different issue. So you can do data augmentation by rotating your pictures or putting some white noise on the picture to make your model more robust. So that was my answer. All right, so moving on. So as I said, this is the second strategy to analyze your model, which is to do gradient descent on your input, not your model parameters. Do gradient descent on your input to maximize the activation of certain nodes or certain filters. And so you can see that these are all different inputs that activate different filters. So some filters focus on like I guess this is kind of a texture type of thing. Like some filters focus on like I don't know, like can we call this diagonal? Like this is kind of like looks to me like a horizontal texture thingy, and this is more like diagonal, I guess. And some focus on different colors, like purple, green, because we're providing like RGB pictures, the pictures with actual colors. So it should focus on different colors and different textures. Yeah, these are very like hard to. I mean, to human eyes, these like inputs don't really make a lot of sense. But again, this is how convolutional neural network, the deep learning model, perceives the world or perceives the pixel images. So this is like first block, second block. I guess it's more a bit higher, like more abstract now. Like before, it was very basic, like noise-like signals trying to pick. So the like lower layer was trying to pick up like noise level or pixel level detailed signals or detailed patterns. So now it's a bit more high level. You can see that some filters focus on dots, I guess. So it's no longer just like weird like waves or weird like I don't know what to call this. And it's a bit more friendlier towards the human eyes. And now, okay, even more. So this is the third layer. So I guess we can try to interpret some of them. Like this filter especially focuses on like diagonal like edges, and this filter focuses on like vertical edges, and this filter focuses on, I don't know, like bright patches or something like that. Okay, now, yeah, this becomes more like, I don't know. Can you call this these cat eyes maybe? Yeah, I mean, they're trying, you can maybe say that they are forming a structure. So the lower layers were picking up on like features or edges. And now the higher layers, higher convoluted filters are trying to pick up or compose like a human readable structure. And then if you go higher and higher, then you'll start to see like cat-like images. Actually, I do have something interesting to show you. Give me just a second. So, I'm trying to open a new a new paper, or not a new paper. It's an old paper. It's back in 2015, 2016, but it's using this kind of like gradient-based approach to show what the filters are learning, and it is a bit more interesting than the blog that I'm showing you right now. Yeah, it's very painful. So yeah, I don't know if it's my internet or if it's just an archive is really slow these days. Right, okay, maybe we can skip this, unfortunately. So yeah, the title of the paper is Understanding Neural Networks Through Deep Visualization. It's written by Yosinski, so he's also kind of a famous name. And maybe if they have different versions of this, 9 versions, ResearchGate. Just click all of them. Okay, now, okay, so this is good, right? Okay, so as I said, in the previous example, we can forget about this. Oh, it's a different paper. Okay, so this is a better paper, I guess. This is the actual paper. All right. Okay, so now we can show interesting stuff. So this is like the still an intermediate content layers, and as I said, it is starting to form a human comprehensible structure. And if you go away, go like more, if you go higher and higher, then at the very end, like right before you make a prediction or classification, if you visualize the if you learn the input so that you can maximize the activation of that specific like layer right beneath the softmax function, you can start to see things like this. So like this is kind of like cat face, like essence of cat face, like how like the cat faces, all the cat images or all the cat faces are looking like this to the confident. Like this is how the model perceives cats. And this doesn't look like human face. I think there were gorillas and stuff somewhere. Right, yeah. So once you train your neural network, we're confident with a lot of gorilla images, then this is what you will see. And this is like different, like these 4 segments are just different ways to visualize or different ways to learn the input with respect to the learned model. And these are just different filters. So you can see like these are pretty like gorilla-like. Like if you see it from like very far away, then you can start to see like it's a bit like gorillas. And like this is just 2 gorillas, 3 gorillas, single gorilla. So maybe each filter is learning different numbers of gorillas in the images. So right, and then yeah, so this is it. So this is a way to visualize the input by doing gradient descent. I mean, visualize the mechanism of the neural network once you've trained it and try to do gradient descent on your input. So the last part is the heat map. So this is a bit new. So this was proposed, but I mean, I guess the idea was floating around, but the most popular approach for doing a class activation heat map or class activation map CAM is from back in 2017. And the algorithm is not that important. We're not going to learn the algorithm, but what it does, what it is able to do with what we can do with this algorithm is that given an image like this, and then we give it to a classifier or a deep neural network, and then suppose that it classifies this picture as like 95% African African elephants, and we want to know why it predicted African elephants. Like what like this is a pretty big picture, and which feature in this picture did the model focus on so that that led to the model saying this is African elephants. And you can use that grad CAM technique to actually answer that question. So if you apply grad CAM technique, this is what you get. Like specifically because of this area, I mean, not entire, like all the others were just distractions, like these grasses, the skies, and even the big elephant here. These were all distractions to the model, and the model only focused on, or not only, but like mostly focused on this specific area, and decided that okay, so this is a picture of an picture of a African elephant, and this is a pretty neat trick. Like you want to get a insight as to why model is making its prediction, and this is a good way to visualize them. And I think the actual predictions was like 95% African elephant, like 1% Indian elephant, something like that. Maybe, yeah, I think, yeah, okay, it's not in here, but maybe it's in the original paper, the grad campaign. Oh, here, okay. So African elephant, 91%. Tusker is like an animal with like this teeth that protrudes from your mouth, like omni. So any, yeah, animals with that kind of like big teeth is Tusker. So it said, the model said 9% Tusker, 0.4% Indian elephant. And the reason for the first prediction is this. And if you can also visualize why it predicted Tusker, if you just change the parameter to your class activation map. It doesn't show here. But anyway, you can still do that. So it's a very interesting concept. Okay. All right, so back to the material. It's already 31. Okay, I'm sorry again. I came to the class late. I was hoping that we could, I guess, by the speed of the progress up until now, I guess there was no way I could finish the entire like 70 or 80 slides today. But still, maybe we could have gone through basics of neural attention. So okay, so I'll just wrap up the class here. From the next class, we'll talk about the neural attentions and how attentions are like very, very popular method. I guess a lot of people are already very, very familiar, and it's especially familiar. I mean, it's especially popular in NLP domain because you can't really visualize. There's no pixel in NLP, so like these kind of like gradient-based approaches are not very applicable to NLP models. So attention is usually a go-to method to gain insight as to what's going underneath the NLP models. So it's very important. So we'll start from neural attention and how to use neural attention to make a healthcare model is also interpretable. All right. Okay. Right. Okay. Okay. So is there any question for the material today? Yeah, all the reading materials if you're interested, you can go to these websites and try to learn a bit more in depth what these different like techniques are, visualizing activation or synthesizing inputs and using class activation maps. So you can do that. All right, thank you everybody. Have a good rest of the weekend, and I'll see you guys next Tuesday. And please don't forget to submit your homeworks. All right, bye-bye.